This is a review of amino acid titration curve. We'll go over glutamic acid as an example in this case. I picked this particular amino acid to review because it has a side chain pKa value, which makes it a little bit harder than the other amino acids such as like alanine, where you don't have to worry about this side chain. It's always good to go over something that's more difficult, so that way you can do the ones without side chain as well as the one that has a side chain. So how you read this table, this 2.19 pKa value is referring to the carboxylic acid group, 9.67 is for the amino group, and 4.25 is for the side chain. If it has 3 pKa values, as you have seen it in the lab, that means we have 3 buffering regions in this particular amino acid. So general shape of titration curve, because it has 3 buffering point, is going to look like one at 2.19. Where's the next one? 4.25, and that's referring to the side chain. And then there is another one for the amino group around 9.67. So let's put those values in. Okay, so one at 2.19, second one at 4.25, and 9.67. Let's start with the most acidic form. What I mean by that is if you were to put this glutamic acid in the most acidic environment where hydronium ion is abundant, it's going to donate most of its hydrogen to amino acid in the places where you can do that. So if you have structure for that, I can scroll down because if we got all the values from here already, we'll draw a structure for this acidic form. So you have central carbon and you have the carboxylic acid from amino acid and NH group, and you have the hydrogen, and I'll draw the side chain. I always want you to remember that this is the backbone, which all 20 amino acid has, and this part right here is what makes amino acid unique. So that's what gives rise to alanine, which has CH3 group, glycine, which has only H as the side chain, and so forth. So if you start off with that, if you remember, this 2.9 was referring to carboxylic acid group. So this is acid, this is amino, that's why we call this amino acid. So 2.19 is always a good idea if you don't want to make a mistake to write down 2.19, and I don't know what just happened here, and the side chain has 4.25 and 9.67. Okay, so we are not going to make mistake. So as you're moving more to the base side, what happens is this hydroxide comes in and start grabbing this hydrogen away because it wants to be neutralized to become water, H2O, because if it gains H, then it can become H2O. So as you're moving this direction, you're getting more and more of COO minus, and the other part stays the same. So over here, you'd get a structure of COO minus, CH, and NH3 plus, and the side chain stays the same. Okay. So the next step is 4.25, and we need to worry about this point. So what do you think it happens? In the beginning, you start more in this form. As you more and more to this direction, this part start getting deprotonated. So you have right here the structure that you see again, this is the predominant structure because as you're moving this to this direction, the ratio of the more basic form and acidic form actually changes. And we'll talk about that after we go over these structures. So you have COO minus CH and H3 plus, and then you would have CH2, CH2, and COO minus after this point. And after that, 9.6 is referring to NH3 plus group. You should remember from SI chemistry that when nitrogen is attached to 4 different atoms, it has a charge of plus. So if you forgot, you should try to do Lewis dot structure, go to the periodic table, and then you should count the valence electron and actually try this out. So if you go past this point, you lose hydrogen from the amino group. That means this group becomes neutral. So the structure over here will be NH2, carbon, COO minus, hydrogen, CH2, the rest stays still the same. The first thing that I want to go over is the overall charge at different point of this titration curve. So if you look at this titration curve, you start off with, you have +1 here, and the rest part is neutral, so you would start with +1. And as you're moving more this direction, you become more and more negative because you're losing the hydrogen. So over here you have +1, -1, and then this is neutral. When you have +1 and -1 at the same point, it's referred to as Zitterion because you have both plus and minus. I think Zitter in German might mean 2. So it's +1, -1, so it's neutral right here. And then if you go more towards this 0, I'll just put 0 here. Then -1, -1, +1, if you add that up, that equals -1. And at the end, you end up with -2. So if I ask you what's the overall charge of this particular amino acid at pH of 8, you should tell me it's -1. What is it at pH of 13? It's -2, and so forth. If you want to analyze this further, just like you have done in the lab, we can look at one more thing here. I just want you to realize that at 2.19, which we said is the pKa value for COOH group from the backbone, right at 2.19 is when the concentration of COOH is equal to the base form of that, COO minus. Over here, you still start having COO minus because you are still influenced by this hydroxide group, but you have COOH that is greater than COO minus. And then what do you think that happens here? COOH is actually less than COO minus. So if you move more to this direction, there is actually a point where you actually have broken this buffer. So you actually have driven this reaction to the completion reaction. The reason why you have different ratios of this is because this whole thing is equilibrium process where it will be the equilibrium between COOH and COO minus. Same pattern follows for the rest of it. So why don't you guys try it out and see if you can really understand this titration curve.